Hi, welcome to part 7 of Applied Maths, and we're looking at combinatorics this time. So combinatorics is about combining things, and the two main ways to do that, at first at least, are combinations and permutations. So this is combining multiple events, and combinations refers to how many different ways you can combine separate things, whereas permutations refers to how many different ways you can arrange selected things, and there's a slight difference, but an important one, which we'll see. So we'll start with permutations. These are a tiny bit easier, that's why. So with permutations, you have a set of entities which can be arranged one of several different ways. And the number of permutations is literally just the number of different ways that you can arrange them. So in this case, the order they're arranged in does matter. So a 1 followed by a 2 followed by a 2 is a different permutation from a 2 followed by a 1 followed by a 2. So permutations would not be used when you're rolling 3 dice and then adding them up to get a total, because it doesn't matter what order they're in. But if this is a loot table, then for instance, option 1 might say look at the gems table, and option 2 might say pick a diamond, and option 2 here is what kind of diamond. And in that case, it's very different from rolling on table 2, which tells you to it's not a gem, it's a weapon. It's a completely different outcome. So you can have permutations with repetition, and what this means is the things that you're arranging are allowed to repeat themselves. For example, if you roll 3 dice in order and keep the order in the arrangement they are, and there's nothing stopping you getting 2 or even 3 sixes, because even though the order matters, you're not removing 6 from the possible outcomes. So in this case, the formula is relatively simple. The permutation formula, so something say PR, permutations with repetition. And the formula for that says PR brackets n comma k equals n to the power k. So the number of permutations with repetition for any system where we have n number of possible outcomes on each object and k number of objects to choose from. So let's say we want, what is it? We want sixes on a dice, do we? So PR brackets n would be number of possible outcomes, which is 6. K would be the number of objects. How many dice are we rolling? And that would be n to the power k. So 6 chances of rolling a 6 with 3 dice. Chances of what number of possible outcomes? Oh yeah, okay. So if there's 6 possible outcomes and 3 dice, 6 to the power 3, 6 times 6 times 6, which is the same formula we've seen earlier, in fact. That's kind of where it comes from, actually. So sometimes the things you're arranging are allowed to repeat. Wait, I've just said this, haven't I? Oh, here's the actual examples. I've just done that. 6 possibilities on a dice, 3 dice, 216 possibilities, possible permutations. But permutations without repetition, in this case, you're not allowed to use the same outcome twice. Dice isn't a good example. Then maybe cards from a deck. So, for example, if you deal a card from a deck, you can't deal that same card as the second card as well, because you've just dealt it. It's gone from the deck. You can't deal it. So the order of the dealt in still matters in order for it to be a permutation. It's not. We're not dealing a poker hand where you can rearrange the cards in your hand. They're still dealt in order, but it's just that we can't repeat the cards. So this is written as P brackets n comma k, or sometimes it's subscript n, capital P, subscript k, different ways to write it. And the formula looks like this. N from P, k is equal to n factorial over n minus k all factorial. So again, n is the number of options you've got, and k is the number of objects to pick. For example, NPK, let's say 3 cards from a deck of 52. So permutations, number of permutations with 52 cards and we're picking 3. It's 52 factorial over 52 minus 3 factorial. So 52 factorial over 49 factorial. I'm not going to sit and do that. That's nearly 100 multiplications. So it's approximately 8 with 67 zeros after it, divided by 6 with 62 zeros after it. So that's 800,000 over 6 which is approximately 133,333. So that's the number of different ways you can deal 3 cards from a standard pack, if the order matters. A more accurate method uses a slight shortcut, and it cuts down on these enormous numbers. Now, you may already be aware of this, but 52 factorial is 52 times 51 times 50 times 49 times 48 times 47, etc. 49 factorial is 49 times 48 times 47 times 46, etc. Now, some of that is the same. We've got 52 times 51 times 50, and then it's times 49 times 48 times 47, which is the exact same thing you've got on the bottom here. So you can actually just do the first few multiplications and ignore the rest. So 52 times 51 times 50, and we stop at 49 because that's all included on the denominator in the bottom. So we don't bother calculating them for either side of the fraction because they'll cancel out. And then you get an exact number, 132,600 possible permutations. Moving on then, the other side of the deal is combinations. And this is written as C brackets n comma k or n from C k. In a combination, unlike a permutation, you don't care what order they're in. So if you deal 5 cards, you pick them up, you can shuffle them in your hand, doesn't matter. It just matters which cards you've got. So in that example, the formula for that, nck equals n factorial over k factorial times n minus k all factorial. So very similar to the previous formula, but with this extra term on the bottom, k factorial. So that's part of your denominator, and as it's a factorial, it's never going to be a fraction. It's always going to be an integer, usually greater than 1. So if you're dividing by a number that is bigger by, well, probably quite a large margin, then the number that you get as a result is going to be much smaller. So combinations are almost always smaller than permutations. So to work out the different combinations in that 5-card hand, NCK would have 52 cards, and we're picking 5 cards from the hand. 52 factorial divided by 5 factorial times 52 minus 5 factorial, or 47 factorial in other words. And let's use that shortcut trick. So we're going to do factorial from 52 downwards until we reach 47, which is a factor on the bottom, so we can cancel that out. But we're still left with the 5 factorial on the bottom. So 52 times 51 times 50 times 49 times 48 is about 311 million. And you divide that by 5 times 4 times 3 times 2. And the total is just over 2.5 million. So that's how many different combinations you can get in a 5-card poker hand. And that's it for permutations. And as this is going to be quite a short video otherwise, I thought I would finish off with what should be part 8, which is how to code various statistical functions. Now these are all standard functions, and I'm sure with a little bit of Googling you could find them online, which is why I've just collected some here. I've kind of done that Googling for you, and you can see how strong my Google foo is. Now there is, I should mention, an average function built into the C# libraries. You take an enumerable type, which means anything you can enumerate, like a list or an array or something like that, and you can do dot average, and it will work out for you. But that's kind of cheating because we're here to learn how to do this kind of stuff. So here's how to do a mean, and that's the formula for mean on the left we've seen before. Add up all the x values and divide by how many items you've got. That is your mean. Here's how it looks in code. The sigma almost always that means that a for loop or a for each loop of some kind, and that's what we've got here. So we start with the mean equals 0. To be honest, I probably should have said running total equals 0 because it doesn't become a mean until you do the final calculation. But anyway, so we start with 0 and we go through all the values one by one and add them on. And when you're finished, you divide by the length of the array, how many items you had in there. Simple as that. So this is mean, it's what people usually call the average. And then we've got median, which is the middle value. And remember, there's 2 different ways to do that, depending on whether there's an odd number of items or an even number of items. If there's an odd number, you just pick the one in the middle. If there's an even number, you pick the ones on the left and right of the middle. And by the way, that formula is slightly wrong. It shouldn't say n plus 1 over 2. It should say n over 2, then plus 1. That's what I got wrong in my previous video. Sorry about that. So we've got a median variable, And if you take the number of items in your array, your input data, and that little percent symbol means modulus, and it basically divides by that value and takes the remainder, not the answer. So if you divide by 2 and you're left with 1, so anything with a remainder of 1 when you divide by 2 must be an odd number. So therefore, we use this formula. X, oops, sorry, can't double click on code when you're not in the editor. We take in our array, which is X, the values, X values, and pick out N divided by 2. We don't need to do plus 1 because arrays start at 0. So that cancels out. So that is your n plus 1 over 2 in there. And that gives you your median. But if it's not an odd value, then we take x item n divided by 2 minus 1, because if we didn't need the plus 1 up there, then we need the minus 1 there. And then the next one is just x n plus 1. Add those two together, that's those two up there, and then divide them both by 2 to get the average between the two. It looked complicated, but it is doing the exact same thing. It's just picking the two on either side of the very central part of the array and averaging them. Now, mode is a pain in the backside. There's no simple way to do it because it's not really arithmetical. I'm going to use a thing called a dictionary here. Now, a dictionary is basically a list of items, but it's a list of items with two parts. On the left, you've got the actual item itself, and on the right is some sort of key associated with the item. Now I'm going to use it. Here's the actual numbers in our input array, and here's how many times that number appears. So I'm going to call it the counts. So we're going to count each number, and that's our set of counts. So there's two parts here. First, we count the number of occurrences of each value. So go through all the values, and if our dictionary contains that value, then we increase the integer part, the number of times it appears. If it's not in our dictionary, then we add it to our dictionary by starting at 1. So it goes through all of our input values. Let's say we've got 3, 4, and 5. 3 isn't in the counts, so the number of times 3 appears will now be 1. And if we find it a second time, it will go up to 2. Anyway, so that fills our dictionary with, here's all the numbers, and here's how many times each number appears. So the second part then is to go through that dictionary and find out which one has the highest number of appearances. And that will be our mode. So to do that, we also need a thing that tells us what the maximum number currently is, and it starts at 0 because we haven't found any. So we go through all of the keys in our dictionary, and if the counts for that key, how many times it appears, is greater than the current maximum, which starts at 0. So the very first key in there should beat the maximum, and that will be our new maximum. And we found a mode. Keep on looping through. If you find another key in there which has a number of appearances greater than however many times that first number appeared, then that's our new mode. So it will keep on replacing the mode as it finds something that has appeared more often. And once that loop finishes, whatever's in there should be the one that appears most often. It doesn't work if you've got multiple modes or no modes, or at least it doesn't work accurately. But to do it accurately would be even more complicated, so that's good enough for now. Okay, on to dispersion functions, and range is pretty simple. You take the minimum value, which is, assuming they're sorted, it's the one on the left, the 0 value, a 0 index value, and the one on the right will be your maximum. So take however many values there are, let's say 10 items. If it goes from 0 upwards, then it won't end at value 10, it'll end at value 10 minus 1, which is 9, because the first one is 0. It goes 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. That's your 10 items. So you've got your minimum number and your maximum number, and the range is just the bigger one minus the smaller one. That's all you do. Okay, so variance though, the function looks more complex, and it definitely is. So first of all, you have to get the mean, which you can do using the code that we saw a couple of slides ago. And the variance then starts at 0, loop through all of your values. That's the sigma part appearing. And the variance goes up by adding on power of 2, so something is squared. What's squared? Well, x minus mu, there's x, that's our current value, and mu is the mean. So the distance to the mean is squared, and we add that on to the variance. Now, at the end of it, divide by n. There's actually two formulas for this. I didn't show you the second one, but that was n minus 1 if it is a sample instead of a whole population. So if the data is sampled, you divide by n minus 1. If it's not sampled, you divide by n. That is more, I think that's one of the more complicated ones we're going to see. Standard deviation, it looks even more complicated because it's the exact same thing but with a square root around it. But once you've done all the code from the previous slide, all you need to do is take that variance and give it a square root. You've got the standard deviation. Now the mean absolute deviation, this is, oh hang on, it looks like this, but this variance you see up here is different from the variance of standard deviation because it's the absolute variance. So we look through all our values, there's a sigma appearing, but it's x minus x bar, so the variance goes up by adding on the absolute value, that's those lines on either side indicating absolute, so the absolute value of x minus x bar, the mean. Keep on adding that to the variance, so if our, let's say our current value is 10 and the mean was 5, 10 minus 5, we're 5 units away. Next value might be 3. 3 minus 5 is negative 2, but the absolute makes it 2. So each time you're adding on a positive number, you're not going to cancel them out. And overall, our final mean absolute deviation is the total of all those variances divided by n. And last but not least, we've got standard error of the mean. So standard error of the mean is standard deviation divided by the square root of n, which is the number of items in your data sample. So SEM equals standard deviation, which you had to calculate in advance, divided by the square root of n. Now remember, standard error of the mean is only used in samples, because if you've got a full population, there is no error in the mean. You have the actual mean because you have all of the data. But if you've got a sample, you don't have all the data, and the mean you calculate from the data you do have will be not quite right. There'll be a little bit of error in it. So this will tell you the standard error of the mean. And last but not least, let's see some of that in action. Now I've got two data sets here, two different samples, and I'm going to pick one of them. I'm going to use samples 1 for now, so I can swap between them quite easily just by changing that to samples 1, 2, or whatever. We'll list out all the input data on the screen, and then we'll work out various things, the mean, the median, etc. So here's the code for the mean, which I just showed you, the median, the mode, range, variance, standard deviation, mean absolute deviation, and standard error of the mean. So why am I bothering to show you all this? Well, they do tie together. So if you work out the mean, don't worry too much about the median and mode because they don't really tie to anything else. But if you've worked out the mean in advance, then when you get to the variance, mean is reused because we calculated that. Should be still highlighted. Yep. Mean calculated up there, and it's used later on when you do the variance. Now, this is all done in one big function, but realistically, if this was a library or some kind of code that was not a one-off, you probably want to put them in functions and pass that in as parameters. But then we're working out variance, and that variance can then be used within the calculation for standard deviation. And standard deviation can then be used in part of the calculation for the standard error of the mean. So the output of one function can be used as the input of another. That's just function composition for you. Quick run of it. You'll see what's going on. So here's our sample data. The mean, the average is 21.64, somewhere about there. The median one, the one in the middle, is this guy here. So he's our average guy. The mode, though, is 28. It appears twice. The range is the distance between 10 to 34. So that's our range, 24. The variance is 79.05952. What does that mean? There's no numbers here that really relate to that. It's not very useful, but I'll come back to that in a sec. Standard deviation is the square root of that, 8.9 roughly. And that kind of tells us that the majority of our data is no more than 8.9 units away from our mean. So most of it will be somewhere between 13 and 30. Yep, that's true. Mean absolute deviation, 7.2. And the standard error of the mean, 3.36, which can be used to calculate how our confidence interval, how confident are we that mean is close, that mean is close to the true mean if we had an overall population. Oh, sorry. So the variance was the one that we didn't really know what it meant, 79 roughly. Pick a different data sample. So we're using samples 2. And it's got a variance of 83. So all that really tells us is that this sample of data is more dispersed, more spread out than the first sample. So it's really only used for comparison or to then calculate standard deviation. And that will do for statistics for this time being. Thank you.